last lecture, and today we are going to speak spin-wave data processing, spin-wave-based data processing. So what do I plan to present here? Just general ideas. So over the last years, people were trying to find a way how to build more or less Magnon computer or how to process binary data using spin waves. Originally, spin waves were used for processing RF RF information, so analog data processing. But then there was many attempts and interesting research done in the direction of binary data processing. So I will give you a broad overview. I will be quite fast because of limited time, but we will have, you will get a taste actually how it works and what are the main ideas. What's the general motivation behind is, of course, CMOS complementary metal oxide semiconductor technique. What will be its future? So there is a Moore's law, which is actually not physical engineering law, it's more about finances. Moore is one of the people who created Intel company, and he said at some point that every 2 years the number of transistors per chip should be doubled. And this would be the best progress speed of the processors, because then you kind of always give on market new product, but at the same time you're still able to follow it, and it's best ratio. And over the 40 or so years, 50 already, Moore's law was really working and everything was on the line. But over the last years it's getting harder and harder to make elements smaller, so Moore's law starts to saturate, so it's not so easy to do it. Also, if you speak about clock rate of devices, you see that it stopped around 3 gigahertz already 20 years ago. I still remember times when speed of computer was doubled more or less every year. But this one it was already saturated. And so the future of CMOS, of course, is under the question, but on the other hand side, you should be always very careful with such statement, because CMOS always finds a way, it always develops, and I'm pretty sure it will develop further. And it's amazing technique. Nevertheless, people are thinking what will be after 50 years, or long style. So will mankind will be forever with CMOS, or there will be something else at some point? And this is a good background for physicists to search for new ways. If it's possible to propose something conceptually new, like quantum computer, for example, or neuromorphic computer, something which would work even better than CMOS, so it can be merged together with CMOS and to do some concrete tasks. So that's the general motivation behind the studies, and just a very basic slide, which everybody of you knows. But maybe you have seen this joke that 10 out of 3 people do not know binary system, So binary system is nothing else that you need to have 2 states, 0 and 1, lamp is off, lamp is on, or any other 2 states you want to have. And then 1 bit, it's simply 1 lamp, yes, no. 1 lamp would be, take 1 byte, which is 256 states, so 8 bits. So I took this book, a large one, 3 volumes. Here it's just very simple. I just checked on a book what is the size of file. Of course, the size mainly is given by pictures, something else, but that you have a feeling how many bits you need to code data into something. And then if we speak about numbers, for example, if it's smaller than 2, then you need only 4 bytes, and here's decimal numbers, and here is binary numbers. You see that you need more and more bits, the larger number is. And here you see that actually this is the answer to the joke, that 2, this 10, it's in decimal case means 2. Therefore this joke was about the 2 out of 3 people do not know binary system. Good. So that's just very basic. So binary, why I give it to you? Because principally it doesn't matter what we use to code data. It can be anything you want, you need just to find 2 states. And then next step is you need to define truth table for your element. For example, AND gate, logic gate, it means that you have 2 inputs, A and B, and you have 1 output X. and this output depends on the logic input. So for AND gate, it means that there should be 1 and 1. So two of them inputs should be 1, and only in this case it will be 1. For all other cases, it's 0. If you have OR gate, it means at least one of them should be 1. So 0, 0 gives you 0, and this will be 1, 1, 1. What to code in the data? For example, if you will go to YouTube, you will see a bunch of different videos how people do logic gates with wood or whatever. For example, this one with water. You have this kind of pipette where you can press button, and you have two types of water, transparent and black. Black means logic 1, transparent means logic 0, and then you have this simple complicated complex structures where liquid flows in different directions, and principally you can make quite complicated logic gates simply with water. If you do the same but on micron scale and a bit more complicated, you can publish it in Science. So principally also very interesting approach. So you see it was interesting for community to do this logic. Of course, they do not pretend to compete with CMOS, they can directly write it, but still physics behind is interesting and it can be used for different cases. And idea of spin waves is, of course, also let us use spin wave instead of electric current to process data. What is in electronics? So in electronics, we use density of electrons which are moving. We have electrons, it's logic 1, there is some voltage. No electrons, it's logic 0. In spin waves, you can do it in the following way. I have precession, it's logic 1. I have no precession, it's logic 0. One way. But when you have precession, or when you have such a wave, spin wave has additional degree of freedom as a phase. And I will show you a few examples when this phase can give you additional, very powerful degree of freedom that you can process data with smaller number of elements, for example. On top, this stays here to symbolize nonlinear Magnonic processes. So spin waves are nonlinear, and it gives you additional degree of freedom to process particular binary data. And then, yeah, when you this is all wave-based computing, so it can be light, it can be sound, it can be anything. And then you need to choose which wave you want to use to replace electric current. And here you are, of course, free, but you need to be able to do the job at 10 nanometer scale, because you want to add something to CMOS, and CMOS already is there, sub 10 nanometer, so it should be very small, and there is not so much choice. So light has too large wavelengths. X-ray you cannot control at the nanoscale. Acoustic wave possible, but they will be damping, isolation, and other problems. And second, you need nonlinearity, and spin waves are strongly nonlinear. Therefore, principally, Magnon seems to be a quite good choice, particularly for processing data. Well, plasma and polaritons also very interesting, but when you go to nanoscale, they have zero velocity, so they do not run, they do not carry information, cannot use them. But spin waves, the shorter the wavelength, the higher frequencies, the faster they are getting, everything is kind of getting just better. So, where the story started? Started the story with Ricardo Hertel, known person in terms of in micromagnetic simulations business, and in one of his work he has simulated this interferometer with two arms, and he added one of the arm domain wall which changed phase by pi, and he has proposed that this potentially could be used for the realization of spin wave logic when you have constructive or destructive interference, and you can have 0 amplitude at the output or 2A amplitude at the output, and he said that this can be used for logic. Principally, not much more than that, but it was a beginning. And it was 2003. And then in 2005 already a group of Burkhard Hillebrand, so Michael Kostel, Alexander Strihaz, they have shown this spin wave logical gate when they, instead of using domain walls, they made a phase shifter simply by two antennas, like we discussed, propagating spin wave spectroscopy. But here was a wire through which DC current was sent to modify biasing field locally. And dispersion was locally changed, phase accumulation was changed. So principally they made phase shifter experimentally already and said that it can be used for logic. And then next device, already first prototype was shown by Thomas Schneider at the same group. And the device works like this: two spin wave waveguides, two antenna to excite spin wave, to detect spin wave, Here you use microwave signal to split, here microwave signal to merge two signals, and then two loops through which you can send current, input 1, input 2. And when you send current, you locally change Ørsted field here, and you remember you shift dispersion up or down when you change dispersion. And when you shift dispersion while keeping frequency constant, it means you change wavelengths. And wavelengths means that there will be phase accumulation. They measure this phase shift as a function of applied current, and then have selected such point where phases change exactly by pi. And then they have realized exclusive NOR logic gate. How does it work? So input is your DC current. You have current, it's logic 1, no current, it's logic 0. Output is your signal here, micro signal excited by spin waves. 0 and 0 means nothing is applied here, nothing is applied here. Two spin wave pulses propagate, they run. They detected that this is this antenna, signal is merged, signal has the same phase, output is 1. That's what they measured in experiment. In this pulse regime, they see spin wave signal 1. If you have 0, 1, it means that this one propagates, but here you change phase by pi. Signal detected here is shifted by pi. There will be destructive interference here, and output is 0. 0. If you change phase to this one, again will be 0. So you have 0 and 0. And if you change phase of both of them, you will have, again, construct interference, and again you will have 1. So this was the first experimental demonstration of spin wave logic gate. Good. The same idea was used in this paper of Lee and Kim when they use such interferometer and send current through the wire when they change locally field around, and they could get constructive or destructive interference, and also has shown that it can be used for complicated logic. The problem in all these approaches is that input is DC pulses, so current, and output is magnons. So it means that if I want to do integrated circuit, the next step I need to read out the signal here or here, and I need to convert it somehow into DC current here or here. And this converter can be much, much larger than your transistor, for example. Therefore, it's a big issue was how to go towards integrated circuit, because you need somehow to convert it. And that's the main idea standing behind this Magnon transistor. Actually, I was searching really for that some years to try to find such a way, and then accidentally, while doing another experiment, we have found this transistor functionality. The idea is very simple. So this is animation was made for CEBIT exhibition. We were presenting transistor for general public. It was very fun. Politicians sent us there, and we made this animation. So transistor has three places: source, gate, and drain. And what you want to do, you want to send signal from source to drain. So you apply kind of voltage. This blue bubbles is your transistor, and when they reach this point, there will be maximal signal. So transistor is open in the easiest case. That's how it works. Now our task is I need to wait a bit. So now our job will be to control this flow of magnons with other magnons injected into the gate. So we inject into the gate other magnons, red, and they scatter blue magnets. And you see only some of the blue magnets reach the point output, and we see it's half of the current, like shown here. What else you can do? You can send more red magnons, and then you can principally close your transistor at all. So that's what was found in the experiment, and current is equal 0. And that's the main idea, but you understand that here, instead of using DC current, we use magnons. That was the idea. Let's use magnons instead of magnets. So operational principle of this transistor is very simple: to n-channel junction field effect transistor. So it's originally open, and then you close it when you create depletion region here in this PN junction. And it was realized by Magnonic crystal, which you know already very well. Input antenna, source, output antenna drain, and then we just placed third antenna to the gate in the middle of Magnonic crystal. We want Magnon transistor to be open. It means that frequency which we apply to source should be in the band gap. So we choose this frequency and it propagates freely through Magnonic crystal. Red magnons, we want to sit in the region here. Therefore, frequency is different. We selected frequencies that it's inside of band gap. So when you excite it here, magnons are actually not able to run anywhere. They are all localized here. And that's a main trick why we were able to get very pronounced nonlinear phenomena. The idea is the same as in Bragg mirrors. When you have in any laser, nowadays we use Bragg mirrors to keep energy inside. And that's exactly what's going on here. It's kept inside of this non-uniform region, non-uniform simply because of antenna, because of metallization. And it means that red magnons are not able to leave this region. They are living here, and even for small applied power, you have huge density of magnons there. And then what happens, that magnons just propagate when it's open. Nothing happens, it propagates. When you apply negative polarity to this p-n junction, you create depletion zone, you decrease size of this junction here. And the same is this case. Or you can apply larger voltage and you can completely close this channel. And then it's the same if you have many red magnons. So that's the easiest case, and we have shown it experimentally. So some 50 nanosecond pulse was sent to input antenna at the drain after 300 nanoseconds, so it's time when magnons are flying. We could detect such a pulse. And this is without applied signal to the middle antenna, to the gate. And when we apply 1632 or 80 milliwatt to the middle antenna, you see that we can suppress it. And we really could suppress one magnon signal by another. We checked that magnons in BLS are really there. And what the mechanism was is 4 magnon scattering. One input, and 2 other magnons are scattering here, somewhere in dipolar exchange spin waves, and actually we never saw them because they have very large K. We could not detect with antenna or BLS. So that's the mechanism, and on-off rate in this device was 1000 times. And when semiconductor people heard about it, they said, come on, we have already 6 orders of magnitude on-off rate. Why do you believe that it will be better in magnons? And of course, the idea is that it's not about competitive device now. It's like 2 centimeters long. You apply quite huge power. But it was idea if something is possible to do to replace electric current by the magnons, and if it's possible to do all magnon circuits. So it means that no electric signal at all. One magnon controls another magnon, and then we can think about integrated circuit when all job is done purely within Magnonic system. So that was the beginning. Yeah, we were thinking about different types of interferometers with 2 transistors. But actually, at the end of a day of this direction went into the nonlinear directional coupler, which I will show you a bit later, which does all the same job, but much better, with much less energy consumption. Another approach for processing data is so-called converter-based approach. It's so here you can find many papers from IMEC, from TU Delft, from Intel, and idea is that you don't want to replace electric current completely, but you want to do some job within Magnonic system, and then each step you convert it back to electric signal and back and forth. And it was shown that you can do very easily inverter or some majority gate. And in this paper it was shown that principally spin wave device can be up to 100 times better than 10 nanometer CMOS. It's numerical simulations. The problem in this way is that this converter from electric signal to Magnonic signal, they are theoretically predicted to be very good, but in practice it's not yet achieved high efficiency, because if you need to convert each time, efficiency is very important. All Magnon approach is it has many drawbacks, of course, but it's better that you don't need to make this conversion back and forth. Instead, you need to put amplifiers time to time to keep energy of your Magnon level to the proper level. Yeah, so this is kind of 2 ways where it moves nowadays. Majority gate. So what is majority gate? How we are joking, it's the most democratic device ever. It should have even number of inputs, 3, 5, 7, and so on. And the output will give you simply majority. So if you have more zeros, there will be 0. If you have more ones, there will be 1 at the output. And it's very easy to realize it for wave. What you need to do, you need only to change the approach, how you code your data. Idea was proposed by Alexander Hitun. He said, because before we were always coding data into spin wave amplitude. You have spin waves logic 1 and no spin waves logic 0. And he said, let us keep spin wave all the time there. But if you have some given phase, it will be just you select some reference, and then phase difference 0 will be logic 0. And if your phase is shifted by pi, it's logic 1. And why it's cool? Because, for example, you want to have inverter. And that's very easy. You just take your readout device and you shift it half wavelength away, and you immediately get inverter, because phase is changed by pi. And for CMOS, you need to have 2 transistors for inverter. And here we have for free. Another good example is majority gate, because it's all about interference. So 3 ways. Imagine that all of them are in phase. This is 0 phase, 0 phase, 0 phase. Here we'll have 0 phase, yeah, because they construct interference. If you have 1, 1, 1, they are all in interference, the same phase it will be at the output 1. Imagine this one is 1 and 0, they will compensate each other, there will be destructive interference, and the output will be given by the third signal only, and depending if it's 0 or 1, you will have here majority. So automatically for free, more or less, by simply combining 3 waves, you will get majority gate. Is this good or bad, majority gate for logic? Principally, it's very good, because this is your 3 inputs, A, B, C, and output. And what you can do, you can use one of these channels and to use it as a control. For example, you keep it always 0 or you keep it always 1. If you keep it 0, then you have automatically AND logic gate. Or you can have it, if you keep it 1, you can have OR logic gate. If you take your output shifted half wavelength away, you will have NAND or NOR logic gates, which are universal. So principally, you can build all logic, everything what our computer does can be done simply based on majority gate. So it's AND, OR, NAND, NOR logic gate, but also you can do, for example, adders. Let me show you. For example, majority gate, if you would need to create majority operation in CMOS, 3 input, 1 output, you need many devices. You need 1, 2, 3 NOR gates, 4 AND logic gate, and 1 OR with 4 inputs, which is a very tricky one. So altogether it would cost you 48 transistors. It would be a huge circuit instead of 1 combiner of phase. That's the advantage of wave which we have. But people don't really need this majority gate, to my understanding. Therefore, people just do job differently. But there are things where we really need. So AND and OR we discussed. But for example, full adder. In order to build full adder, you would need 28 field effect transistors. Again, huge circuit. Or you can use 3 majority gates and 2 inverters, which we get for free. Much easier, yeah? Therefore, in this case, if you will calculate, you can say that majority gate replaces around 9 transistors. So cool to have majority gate. What people did? First step, of course, Alexander Hitun has published several papers, different approaches. What we did, we brought all this to micro scale, but numerically. Stefan Klingler did it through inputs and just simulated such combiner. And here we had a problem that when spin wave goes this passes, it excites all this higher order width mode. And then when you have here, instead of 1 nice mode, you have many waves with different wavelengths of the same frequency. You cannot read out information. The trick to go around was to make this output waveguide narrower, because then what happened, we could select only 1 wave here, and all other higher order modes were pushed up in frequency and we couldn't see them. And here's animation how it works. So you see large wavelengths here. Then you see complete zoo of different modes, and that's the problem of spin wave. As I said, any non-uniformity will excite you many different modes. You will see complete mess, and it's really problematic to get out nice information. But here, simply by narrowing the waveguide down, we could get such a nice majority operations. So that's one way. So here you see that that's how dispersion looks for first width mode, for second width mode, third one. In 2 micron wide waveguide here, and when you make it to 1 micron, you see that this n equal 2 shifts up in frequency. And you could exclude this parasitic scattering towards the second mode. But you still see this exchange wave, yeah, when it moves up, exchange wave, and here you see this fast oscillation. This is the exchange spin wave. So we still have interference of 2 waves, but less critical than it was in the previous case. Yeah, and then we have shown all the operations for all input phases that principally majority gate works. Next trick Stefan did is we switched from in-plane magnetization to the out-of-plane. Out-of-plane has many advantages, also disadvantages, but one advantage is that you see how spin wave propagates. When it goes here from input 3, for example, it will scatter to all 3 directions. So our dream is that it will go from input to output, but it will scatter also to this way. The same here will be scattered. But this wave in out of plane is non-uniform, is isotropic. Therefore, if you play a bit with parameters, you can already, because it's isotropic, so it means that wave propagating here and here has different angle with respect to magnetization. These are different waves, and this one is different. Therefore, 11% only converted to energy. If you work with isotropic wave, 19% will be converted. But you can make things better if you will change design to this one, to isotropic. Because in this case, you will have situation that majority of energy will be here. Not majority, okay, more than 50%, but not perfect, but better, much better. 64% goes if you will design such a majority gate in the out-of-plane configuration. Another advantage is that you remember this exchange waves create problems. You always can scatter to the short wavelengths if you work in backward volume geometry. And in forward volume geometry, the spectrum looks like this. You do not have exchange waves at the same frequency. That's why you do not have these little oscillations like it was before. So kind of out of plane works better, and it all again was simulated. We have shown that it works. Next step was Tobias Fischer, Betcher nowadays, and we have used this macroscopic YIG fabricated by Igor Severodka in Kiev, in Lviv, in Ukraine. They fabricated the structure for us. And 3 inputs, 1 input antenna, 2nd input antenna, 3rd input antenna, then this mixer of 2 signals, or 3 signals, just combiner, and 1 output antenna. All the same idea. We just need to send 3 signals and to measure output phase of that what is going on. Very simple experimental setup, generator, splitter for microwave signals, 3 attenuators, 3 phase shifters that we can change logical input, and then we just use fast oscilloscope after attenuator and amplifier, fast oscilloscope to see the signal directly. And again, for all different configurations, we have shown that you will get logical 0 when you have majority of logical zeros and logical output when you have majority of the logical output. And who can tell me what is the main problem of majority gate if you look on this figure? Do you see some problem already? Rostislav sees a problem.
The amplitudes are different for the case where everything is in phase and where one is out of phase.
Thank you, Rusty. You're right, you probably saw some of this talk already. So what Rostislav said, that you see phase behaves as it should be, but amplitude behaves differently. If you have all 0, 0, zeros, then it means you have 3 waves constructively and you have very large amplitude. If you have all 1, 1, 1, you will have it large here. And if you have 1, 0, 1, for example, this will be compensated and then phase behaves as properly, but amplitude for this phase is 3 times smaller. So it means that majority gate works once nicely, but if you want to put this output as input to the next channel, it doesn't work. Because next time there will be no interference, you cannot do it. You cannot do integration without normalization of your spin wave amplitude. And this brings us to a very important point, that we need nonlinearity. The point is that why we use semiconductor in our computer, because semiconductor is a nonlinear element. So it means that you can control one signal by another in the simplest case, yeah, or input is not linear proportional to the output. And in this case, we also need this nonlinearity. So there are different ways how you can do it. Either you have this nonlinearity like it was based in this. This is also majority gate, 3 inputs, A, B, C, from IMAC. And here nonlinear functionality is embedded into the conversion. So it means that when you convert a signal from a spin wave to electric signal, you also automatically normalize it. That would be one way to go, and another way to go, you need to find a way to put power normalizer here. But Vasil Tiberkevich once said that even very complicated interferometer will never work as a processor. So you need nonlinearity in one or another way. And here it nicely demonstrates that principally you do need this nonlinearity also here, because without normalization you will not be able to do more complicated data processing. Okay, the last what we did here, we just measured the switching time. We designed such a tricky setup that we can change phase very quickly and within some 10 of nanosecond or so. And then we have shown that principally your response of your signal also changes within 10 nanoseconds or 11 nanoseconds, which gave us a very first taste what would be the clock rate, potential clock rate of this device. And if it's 11 nanoseconds, it's 1 over 10, let's say, gigahertz, it means 100 megahertz. Clock rate would be of such a spin wave computer. Not competitive 3 gigahertz, although if you really can decrease number of elements 10 times, then maybe it's still quite interesting. Good. The last, to my understanding, such a pronounced discovery was done in IMAC. So Giacomo Talmelli and Florent Cheboutaru, Christophe Adelman were behind. They decided that, you see, we have many problems when we make this combiner. And they said, why not to make it inline? So we have 3 input, 1, 2, 3, and they took 2 outputs, and then you also can measure interference between 2 waves. Everything will be simpler, everything is nano, and they have shown it experimentally that it works. Very good design. Good, but I move on, and now I would like to present you directional coupler and half adder. Why did we come to directional coupler? Original idea was that we want to build a half adder. What is this? This is the simplest logic device which has 2 inputs, A and B, and 2 outputs, sum and carry. And it does nothing else as adds 2 bits. So it can calculate 0 plus 0 will be 0, 1 plus 0 will be 1, and 1 plus 1 will be 2. But you need to put C and S opposite ways, and there will be 10. And we will come back to the joke. Yes, 10 in binary means 2 in decimal. But if you are able to do this mathematics, 1 plus 1 equals 2, that's maximum what it can do. But if you put million of them together, you can do any logical, any mathematics. And that was the aim. And we just went to literature and see that half adder can be built based on XOR, exclusive OR, and logic gate, which we knew already how to realize more or less. The question was how to make this cross splitter also possible, but we need to make this cross. And spin wave even in 2D is quite complex. 3D is getting even more tricky. And so we were focused on this question, and Chi Wang did the job. And yes, that's how it's done in electronics. It's very complicated structure. But in Magnonics, we have realized that you can use so-called directional coupler. So directional coupler is well known in microwave business, in optics, used everywhere, and also in spin wave physics. It was shown by Sadovnikov Nikitov for macro scale YIG. Already they made a set of papers on linear and nonlinear directional coupler, and we just took this idea and adapted it to nanoscale. So that's the experiment. They have shown it with brilliant light scattering, more or less a spin wave excited in one waveguide jumps to another and back and forth. So I will show you a few examples. And we did it all on nanoscale and solved several tricks how to guide. So in their case, they use these antennas, and they could not read out information with antenna. So for this, you need to do such a bending of waveguides when you can put antenna separately. And this bending is possible only at the nanoscale, when magnetization follows the direction of spin wave. So this was kind of a path towards Magnonic circuits. Chi Wang has simulated, and how directional coupler works is the following: two waveguides, one here, you put antenna. This one, that's numerics, it's easy. And you excite spin wave in this case. And you see when spin wave propagates, it pumps all its energy to another waveguide, and then back, and it jumps back and forth like it's shown here. So if you plot intensity versus distance along the waveguide, you see that in one point of view, you have maximum of energy in one waveguide, minimum in the other. Then after some period, maximum, minimum, and physically again, two coupled oscillators. So nothing else. We are always speaking about two coupled oscillators when we see this kind of phenomena. How to describe this phenomena in terms of dispersion curves? If you have single waveguide, these are numerically simulated dispersion curves, first mode and second width mode. When you put two of them close next to another, that they coupled due to dipole-dipolar interaction, you will see that there will be splitting of both modes. So it means that if you excite a signal at 3 gigahertz, you have two waves propagating with this case and with this case, propagating in both waveguides. So you always have two waves which run in both waveguides if you have dipolar coupling. But in one waveguide they will be symmetric, will have the same phase, and another mode will be so-called antisymmetric. It will be with different phases. Then what does it mean? It means the following, that when wave propagates, in this case, both waves are in phase, then they propagate, and these waves are getting in antiphase in this point. They are antiphase here, so it means no amplitude, and it means that in the opposite waveguide, they are in phase. That's why it looks like energy is pumped there, although two waves kind of running all the time. But then when you propagate further, these two will become in antiphase, and it means that here they're in phase. Therefore, you can describe it simply in terms of running two waves in both waveguides. Also important is delta K, distance between the splitting here. L is a coupling length, so it's a distance between this point to this point when all energy is pumped from one waveguide to another. And this L is given simply as pi over delta K, where delta K is the splitting, like shown here. So everything is coupled. Clear? Good. So that's the idea of directional coupler. Martin Koenig did the structure. Michael Schneider, Björn Heinz have built a microfocus BLS, which we discussed. And this is a structure, yttrium iron garnet, 350 nanometer wide waveguide. And this is U-shaped antenna. You excite signal here, it propagates, and then you come to the coupling region where there is second waveguide. And starting from this point, we increase spacing in order to decouple. So here they again do not talk to each other, they are independent. And here, this is our directional coupler. And here's a result of experimental studies. BLS, as I said, you can do 2D scan. In CV regime, continuous wave regime, red means large spin wave amplitude, blue means no magnons, because there is no magnetic material here, as you can see. And you can clearly see that for this frequency, spin wave is excited here, it jumps to another waveguide, and it goes there. Then, this coupling length, L, can be easily tuned by changing wavelengths, so or frequency of the waveguide. So you change frequency and you can change how strongly they are coupled. So the stronger coupling between waveguides, the faster, more often it jumps from one to another. Small coupling means it jumps needs some distance. Therefore, if you go to this frequency from 465 to 55, you see completely different behavior. You can split 50% goes to one channel and 50% goes to another channel. Chi performed all measurements and numerical simulations to understand this. If you change frequency more, you have such situations that it jumps back and completely goes down. Back. So directional coupler works. It's all good. How about nonlinearity? I told you that we cannot build Magnon computer without nonlinearity. And we have nonlinearity here, and we have shown it experimentally. But what's the idea? So this is our nonlinear phenomenon. M during precession should be conserved. It means that this end, the spiral lies more or less on a sphere. With excitation of large precession angle, your system behaves like a change in magnetization. So this delta M matters because your spin wave in reality sees not this length, not this M, not this one, but it sees only projection of this magnetization to the original steady state axis. So it means that excitation of spin wave of large amplitude in your system acts on the system like you would change magnetization. So you decrease magnetization in the system. And decrease in magnetization, as we know already very well, shifts dispersion up or down, depending in which configuration you are staying in plane or out of plane. In this case of in-plane situation, we had this following situation. For blue, it's 2 millitesla excited field, and these are dispersion for antisymmetric and for symmetric mode. So this is already two coupled waveguides, yeah? Dispersion is split. You increase excitation field twice only, and you slightly shift dispersion, antisymmetric, symmetric mode. And then you work at this frequency 2282 here. And for us, as you know, the coupling strongly depends on delta K, on distance between this point and this point for blue, for red, and between this point and this point for blue. And you see really that with such a small change in the exciting field, you can significantly change delta K from this one to this one. So you will have one coupling for linear wave of small amplitude, and there will be another coupling, another speed with which it jumps back and forth, rapidness with which it jumps back and forth for a linear and for non-linear system. And that's what we have seen. But in this case, we changed power not not 2 times, but 10 times. It's just experiment. It wasn't planned for nonlinear phenomena. It's just simple directional coupler for linear operations. That's how it works for this frequency, 351 for 0 dBm power. And now if you keep the same frequency but increase power around 10 times, you see that wave when it was going this way, now it goes back. So you could tune frequency, you can tune direction of spin wave transport in one arm or another arm depending on the power. Why is this important? If you think about data processing, of course, energy consumption matters. And in Magnon transistor, remember that it was absorber. It either lets signal through or it absorbs all signal. And this is bad. Here, you don't absorb energy. You always let it go. But if it's small amplitude, it goes to one channel. If it's large amplitude, it goes to another channel. It's just a switch and no absorption. And of course, then it decreases energy consumption for potential operational device significantly. How to build adder. So this is version 2 or 3 already. He is hard working and very talented researcher. He developed several different options. And at the end of the day, we end up with this design for half adder. And it consists of 2 directional couplers. This is one directional coupler. This is another one. This one we name linear directional coupler, non-linear directional coupler. 2 inputs, input A, input B, 2 outputs, sum and carry. And let's see how it works. The first one, actually, it works quite easily. It's just power splitter. So it's tuned in the regime that 50% of energy goes here and 50% of the energy goes here. From this one also, 50 here, 50 here. Important is this nonlinear directional coupler. It has much stronger coupling. You see the space in between is small. That means that we want energy to jump back and forth often. And it's long. So it means that we want to accumulate something. And what does it mean? It means the following, that for a linear case, when we excite only 2 millitesla applied field, it will be jumping back and forth, I don't remember, 8 times or so, like this, and at the end all energy goes to the output 1. Now, the trick here is that it's easy to change power 10 times, and then you would make it without this accumulation. But in experiment, in order to make logic, it was important to change excitation power only 2 times and to get qualitatively different result. And that's exactly what she managed to achieve. That's why this waveguide is so long, because when you change power twice, you only very slightly change coupling length, the distance between this point and this point. Only slightly, so small nonlinearity, small shift in dispersion, small shift in coupling strength. But since it's jumping back and forth many times, we accumulate this nonlinearity, and as a result, this output signal goes all to the output 2. That was the most complicated part. With very small nonlinearity, to find a way how to bring it to qualitative change, that you really change it, that it goes to one or other channel. And then, how further works very easy. We code data again into spin wave amplitude. We have data amplitude, it's red, means logic 1. Nothing is here, logic 0. And 0 plus 0 equals 0 is easy. You send nothing to input, nothing input, here will be also nothing. So this you have for free. 1 plus 0. 1 is going, 50% goes here. Here we just put absorber, we're not interested in it. You can use it for something, but it's not critical now. 50% goes here, jumps back and forth, all goes to output S, sum. This line in truth table is satisfied. 0 plus 1, 50%, back and forth, all the same situation, output S equal 1, C equals 0. The most tricky is, of course, 1 plus 1. It's special designed that phases of these signals are different. I think by pi 2 or by pi, I don't remember, but in this case, all energy will go to this channel. So everything what you excited here, everything what you excited here will go to this channel, and it will be jumping back and forth like we discussed, but for larger amplitude with nonlinear effect, and it will go all to output C. And the last line is a truth table is satisfied. What is missing in order to make it integrated device? So I have 2 outputs, and of course I want to send them as inputs to A and B. Is there something missing? Or we can send them directly? No ideas? Look at the amplitude. You see this red is practically as red as this one. Because what we have here amplitude 1, here everything goes amplitude 2, but we have parasitic reflection from each edge, and we have damping. This is quite long. So it means that amplitude here will be again 1. And you see it here, C equal 1, so it means that this signal output C can go as A or B, just directly for integration. Just go straight without anything. But let us look on this guy. Amplitude 1, here we lost, so 50% only left, and then because of damping and everything, we lost 50% more. So it means that here we have this factor times 4. We need to put permanent amplifier here to keep energy of spin wave from this level to make it 4 times larger, and only afterwards we can send it as input to next device. Therefore, this majority of half adder would be full if you would have amplifier. So we need amplifier. But this is clear understanding. But also it's a very good point because we went so far away and we could finally do benchmarking to understand how promising magnons are and to process data and to compare it with 7 nanometer CMOS. Same kidding, when we started to write when we submitted this paper, 7 nanometer CMOS was just in the plan. It was not on market, and we asked people into Delft who simulated for us a future characteristic of CMOS. But after we managed to get through all referee reports and questions, CMOS was already on the market. Therefore, keep in mind that CMOS also is evolving very fast, and it's fantastic technology. But also, it was cool that we could compare Magnonics to that. First, what we need to keep in mind that in order to make half adder in CMOS, you need 14 transistors. It's a huge circuit, 14 transistor. Even if you use 7 nanometer, the area of it will be like 1 by 1 micron approximately. So it will be a huge circuit, many floors, hundreds of the different elements in there. And it's very complicated. You need to take into account capacitors, delays, and everything. And it works so good because people investigated for 40 years already. So it's simply a super complex but super powerful technique because we need it. And in our case, we have only 3 waveguides plus nonlinear physics plus missing amplifier. Yeah? So principally, you immediately can see that spin wave physics and can replace significantly the number of transistors. Nevertheless, since this guy has to be long, it doesn't mean that this is ultimate limitation. It's just a characteristic of this concrete realization. You can find something different. But in this case, the length was quite long, and we also end up with 1 micron footprint of the device. So it's comparable to 7 nanometer CMOS, but we use 30 nanometer YIG, what we could simulate. And speed. Yeah, speed, when our colleagues, Sorin Kotafara, sent us the data that CMOS can do everything within 60 picoseconds, I was of course surprised. So CMOS is extremely fast, but we never use the speed because we will get troubles with heating. So if clock rate of our device 3 gigahertz, so it means that we need 0.3 nanoseconds to do the job. Yeah, in reality, because otherwise it warms up. But theoretically, it can do job within 60 picoseconds. We would need 18 nanoseconds, so it means we are slower 1 or 2 orders of magnitude in this realization. And energy consumption, CMOS, they said that it would need 35 attojoule, and for YIG we would need 2 attojoule only to spend energy within Magnonic system. So Chumak gives you this information directly, so we can get energy. But you still need amplifier. And then we started to think which amplifiers we need. We tried spin orbit torque based amplifier. It's very separate, complicated story, but we won't get proper energy consumption. If we have a parametric pumping based but current based amplifier, it would work. We have shown that it works at the nanoscale, Bernheim has shown, but we would use 10 to the power 5 attojoule. Again, we are not competitive in terms of energy energy consumption, but VCMA-based, voltage control magnetic anisotropy-based parametric pumping seems to be the most promising. Roman Verbach has shown it theoretically with Andrei Slavin that and this is 3 attojoule is a prediction theoretical one, and I think the closest is Ilya Krivorotov and Yoshishi Kotani, who are working in this field. Krivorotov has published something similar, but it's not yet fully functional as it's expected to be. But let's say this VCMA-based amplifier still has to be realized. It's very important for the whole, this all Magnon data processing. Yeah, here is actually the paper of Ilya. And here is a theoretical paper where it was predicted. Good. And I'm ready to come to give you a very first flavor about inverse design Magnonics. Other questions to directional coupler or no? Okay, so to summarize what we have here, what this table tells us about my personal opinion, everything what I say here is just my own vision and understanding. Principally, I have seen many technologies which were trying to compete with CMOS, but some of them were working in hertz range, some of them used ampere currents. It was really hard to... CMOS is so good that it's practically impossible to compete with it, to my understanding. Therefore, if some parameters are getting close to CMOS, it's already a great success. Therefore, Magnonics principle is much better than I expected 5 or 10 years ago. Nevertheless, it's not sufficient to wake up industry. So we discussed with Intel people and so on. They will not start moving in that direction unless these numbers will be significantly better than this one, better 100 times each of them. And this technique Magnonics cannot give it at the moment. Nevertheless, we've got a reinforcement where we believe we should be able to improve all numbers at least 10 times. Andrii Chumak is here, that's his PhD thesis. Very nice task, because now we want to use inverse design Magnonics. And how does it work? So principally, there were two papers. So Chumak and Philip Pirov did this job together, but also Georgi Ksaba was the PI in another paper which was published or submitted simultaneously. We made parallel this inverse design Magnonics, and but idea originally came from optics. At least we paid attention from optics, and this looks the following. For example, you want to make demultiplexer. It's a device with one input and two outputs. You send two frequencies, F1 and F2, in linear regimes, and they don't interact. And you want F1 to go to this channel, F2 to go to this channel. And this is your region. And what you do, you just say that I take it 1 by 1 micron, and I split it in such regions 100 by 100 nanometers, so matrix 10 by 10. And then what I do, I randomly remove yttrium iron garnet and make just holes here. Just made it, and see how much F1 and F2's energy goes here and how much F1, F2 goes here. And we did it simply numerically. Then you do more or less algorithm. So you initially create such voids where you remove YIG. And then, so I don't go through the scheme, but it's very straightforward. What you do, you randomly select one of these elements, and if it was air, you replace it with YIG. If it was YIG, you replace it with air, and you again simulate how much F1, F2 goes here, and how much F1, F2 goes here. And then you check if system became better or worse. And for this, you need so-called objective function. So you can define it in a different way, but more or less the trick is that you need to convert that's what I said by words, that I want to have here F1 only and no F2, and I want to have here F2 only and no F1. You convert it simply to mathematical formula. So in this case, it was simply intensity F1 output 1 minus intensity F1 output 2 multiplied F2O2 minus F2O1. And then you changed one of your elements, and you again perform simulations. You see how much energy here, how much energy here. For each frequency, you calculate objective function. If objective function became better, you leave this position. And then you randomly select new void. If worse, you come back to the previous case and you randomly select any of these other elements. And then one iteration means that all of these elements were tested and checked back and forth in a random manner. And then second iteration means that you just started again the same, but you see that already after first iteration, objective function was increased immediately, strongly, and then only small improvement. And then at the 4 iterations you had, instead of this initial configuration, you have this position of voids. And if you will see spin wave, how they propagate, 2.6 gigahertz goes to up, 2.8 gigahertz goes down. Exactly like it's done. Like you expected, it works in some frequency range, everything is perfect, very good device. And you can make multiplexer, so again you can simulate it. That input from this channel for this frequency goes to output, and this 2.8 gigahertz goes to output. Everything works perfect, and the great point about inverse design is that you don't need to know what is inside. You need just to ask computer properly to optimize the task, to do the optimization for you. Yeah, and here are some animations, how the multiplexer and how multiplexer works. Everything is expected. Good. I told you cannot do nonlinearity. You cannot do computer without having nonlinear element. And then what she did, he said, let us keep now frequency fixed, 2.6 gigahertz, but I want to have two powers, 0.5 millitesla and 2 millitesla. This difference 4 times, that we can still play with this interference like it was in the directional coupler. And then he has found that it doesn't really work unless you increase the region twice. So here he has matrix 10 by 20, because nonlinearity it needs some time and to accumulate, and it was necessary to increase the region a bit. This matrix was too small, but afterwards all the same algorithm, you just need to change objective function. So now you say that if I apply small power, I want it to go to B1. If I apply larger power, I want it to go to B2. And after simulations, computer easily has found such configuration, and we have it. And then, yeah, so everything works perfect. And it was kind of, he was impressed by the strength of the inverse design. That's why we now invest a lot of time and efforts in this direction. We see that there is a big future for this direction. And you see this is not as big and not as long as that 6 micron or so long directional coupler. Yeah? So we can now improve footprint significantly. That's why I said that we expect improvement in all parameters at least 10 times, because also delay will be decreased. Spinwave don't have to run such a long distance. It's now just 2 micron. You can make everything much faster. Then what we decided, okay, spin waves are known to be non-reciprocal. There are many non-reciprocal phenomena. Let's ask computer to make Y circulator. So what means Y circulator? Port 1, 2, and 3. When you apply something to port 1, it's fixed frequency, it goes to port 2. When you send the same signal to port 2, it goes to port 3, and nothing goes to port 1, and from 3 it goes to 1. And we just ask computer to optimize it, to find such configuration when we can get this Y circulator, and it works. And only afterwards we actually realized that it should not work. Because in this all simulations we were working in out-of-plane magnetization with so-called forward volume waves, and they are known that they are isotropic and they are reciprocal. So wave which is run in one direction is exactly the same as in the opposite. So it was a question, why do we actually have non-reciprocal phenomena? And then we had to go back. We made such a waveguide which was magnetized out of plane, and we see what are the properties for wave propagating in one direction and another, and we have found that there is a very weak change in the distribution of intensity versus width for wave running in one and another direction. And then we have realized that in our case, the width of the waveguides is getting comparable to thickness. Therefore, strictly speaking, we are working in forward volume geometry, but if you just look on the same picture from side, it's Diamond-Eschbach. Simply because width is getting comparable to backward volume. Therefore, in reality, what we have got here this small feature coming from the nature of the Diamond-Eschbach from magnetostatic surface spin wave. It's very small, we would not notice it, but computer managed to accumulate this very small phenomena, accumulated in order to get a nonlinear phenomena. Non-reciprocal phenomena. And this is a very nice example when, especially in the view of ChatGPT and all other things, you see how fast it's developing because it's all about the same. So this is a nice example when a computer pushed us not to discover a new physical phenomena, but something what we did not expect from the physical point. But it works good, yeah, and then we checked how it works when you change polarities, that its operational principle changes, so everything as it should be. Yeah, so principally this is the last slide. What we did, we checked how robust is the structure to the fabrication mistake, so we randomly changed the sizes of this void. It's quite robust, good technology, prepared everything for the fabrication and for experimental realization. We are in process now, and we also have shown that you can decrease sizes of all this 10 times, and then everything works even better. So the smaller structures, the better it is for Magnonics. So Magnonics is perfect for the scalability, and yeah, as I said, it's very nice direction, and we have tried several ways to implement this inverse design on experimental way. Principally, I'm ready with this lecture. Other questions or comments? I see no, then let me finish the lecture course with these formal slides. So Andrii Chumak was working for you. This lecture is given at the Faculty of Physics, University of Vienna. Cool faculty with very rich history. We are recording this lecture somewhere here. Erwin Schrödinger was sitting somewhere here. No, here, sorry, fourth floor. Anton Salinger, I think his office is over there. So it's very cool faculty. And I would like to thank with the last slide to Rostislav Zirha, who made all these fantastic Blender animations, to Andrei Warren, who helps with 2D graphic design, and Pedro Del Real, who is doing editing of YouTube and staying behind principally all these activities. As I discussed, we principally make all these animations and nice pictures open for you. You will find this link is in the description, so if you need it, go ahead to use it. And with this, I would like to thank you for your attention.